Good day! You might be wondering what this portable apparatus for in-situ thermal response test is. Me, Hannah and Bashir and my colleagues Shamsa and Serena from the mechanical department, and we are going to discuss what it's about. So let's start. This is our testing device, and what it does, it's actually testing the soil characteristic and properties to check if it's suitable to install the ground source heat pump. Why we need that? Because we want to replace the AC conditioner to something which will be more eco-friendly and less pollution to the environment.
Thermal response test. The first step is to inject or extract heat from the borehole heat exchanger. Then, the heated or cooled liquid is circulated through borehole heat exchanger and back into the TRT apparatus. Then, the change of the fluid is measured to give three properties of the soil. So, what are these properties? First, undisturbed ground temperature. Second, ground thermal conductivity. And third is the borehole thermal resistance. And now my colleague Serena will explain to you how we obtain the soil properties.
So, how do we obtain these soil properties? First of all, for the undisturbed ground temperature is simple. So for 24 hours, we do not attach any heat load, we just run it through the system, and once it completes one cycle, how it behaves at the borehole outlet will be measured, and that will be the outlet temperature, the underground undisturbed ground temperature. Then to get the borehole heat resistance and ground thermal conductivity, we run the temperature values after recording it over a couple of days. After logging the temperature values over a couple of days, a logarithmic line will be passed through the system, and then we get these values. So Hannah is going to tell us how our system works.
And now I will be explaining to you our mechanical system. First, the water gets through from the inlet pipes through the flow meter that measures its flow rate, then to the thermometer that measures the temperature of the inlet water, then the pressure sensor that measures the pressure of the inlet water. The water then goes through circulation pump and filling pump, pushing the water to the expansion vessel. The water in the expansion vessel gets pressurized, and here as you can see we have a pressure stat. What is the job of the pressure stat? When the pressure drops in the expansion vessel, the pressure stat will turn on the two pumps. And if the pressure in the expansion vessel is high enough, the pressure stat will turn off the two pumps. Then the water goes through the air release valve. The air release valve will remove any excess air in the pipes, and the water will go to be heated through a heater. As you can see, we have insulating pipes here to prevent the heat to travel to the expansion vessel and damage it. Here is our physical prototype. As you can see, it's exactly similar to our 3D CAD model. And now, my colleague Serena will explain to you the control system.
So the way it works is pretty much simple. So the fluid that has entered into the test rig will be heated. So the heat load is injected into the heat exchanger and then passes through the ground in which the heat is lost because the ground is of a lower temperature than the heated temperature. And so the cooled liquid passes through the entire system and completes the cycle, goes through the cycle again. So there is a process that the heater undergoes to keep it under certain temperature ranges from 40 to 42. And this process is actuated by a relay, and the energy consumed by the heater is also counted by an energy counter. So these entire processes and the sensors, the temperature and the pressure that are sensed, both at the borehole surface and in the environment, is then sent to the microcontroller. And Hannah is going to tell us what exactly goes on in this microcontroller.
Okay. Our electricity diagram, we connected all our sensors in the Mega Arduino. We use Mega Arduino because it has a lot of pins, but still we were running out of the voltage and the ground pin. For that, we connected to the breadboard. As you can see, these are our sensors. We have two pressure sensors to measure the pressure, two thermocouples to measure the temperature in the inlet and the exit of the borehole, and one flow meter to measure the flow rate, and Bluetooth modem to give us the output reader in our tablet to see the results, SD card to save the results, and RTC to measure the time, and humidity and temperature sensor to measure the ambient temperature. Lastly, the heater. Actually, we wanted to connect the heater manually, then we thought, why not to connect it electrically? Then it will switch on and off automatically by using relay, and we coded to switch on when it is 40 degrees and to switch off when it is 42 degrees. So that's it for the electric diagram. So now my colleague will explain.
So saying that we do not have any experimental results, we are able to calculate it based on the theoretical things available, which was based on the infinite line source model. So this was based on the one-dimensional heat conduction equation to get the mean fluid temperature. So this equation was then solved on MATLAB by using different assumptions of standard measurements from previous research, like the ground thermal conductivity and the borehole thermal resistance we assume to be later verified when we have gotten the results in our experiment. So please tell us what these results mean.
These graphs were obtained from the MATLAB. As you can see in this graph, we have different flow rate, and as you can see, when the flow rate is 20 liters per minute, it has less mean fluid temperature difference. But when it's increased to 120 liters per minute, it has huge difference in mean fluid temperature. In this graph, as you can see, it's flow rate versus temperature difference in the inlet and the exit. And as you can see, when it has less flow rate, it has the highest temperature difference at this point, which is almost 50 in the flow rate and maybe 0.55 in the time difference. And this is our simulation that we got from ANSYS. As you can see, here we have the borehole depth, and it is 25 meters, and the material weight made from the polyethylene, and it is single U shape. And this is the borehole. Here the heat injection entering here, and it's exiting from here. As you can see here from the back side, it will enter here and the heat will keep losing its heat till it exits. Now my colleague Shamsa will explain about the cost analysis.
For the cost analysis, to begin with, we had some components that already existed on campus from previous projects, such as expansion vessel, 2 pumps, and PCB. This is why we didn't exceed our budget given from the university, which is 3,600 dirhams. Our total cost of the additional components we used to make this project suitable for our design costed 2,648 dirhams. We didn't exceed the budget, but we wasted some amount of money because we wanted additional components that we didn't use because it didn't fit our project or didn't work with the idea of the design.
So now we're going to show you how this system functions. So, having explained before, the water flows in here, goes through this system, goes out, and then the borehole piping will be connected to this part, and then there's going to be a continuous circulation. And how these values are sensed will be shown to us now.
We're going to connect the laptop to the Arduino.
To initialize the code.
Yeah, and we connect the tablet to the Bluetooth. So we are getting the result in the tablet, as you can see. This is the pressure, the temperature in and out, the temperature of the ambient, humidity, and the flow rate. But
it also shows the time.
Yeah, the time. And actually it shows some value 0 because it's not connected to the pipes, that's why.
In conclusion, in the quest of finding sustainable methods to provide air conditioning, companies may utilize our TRT to inspect the soil and install front source heat pump that will reduce the electricity bills and the emissions. Thank you.
Thank you.